Okay, in this video we are going to finish this practice quiz. So we've done problems 1, 2, and 3. They're in parts 1, 2, and 3 if you look in the playlist. And there's a link to the quiz in the description, and we're on problem number 4. So let's see what it says. So we want to write two different integrals that give the total area of the region enclosed by the outer loop of r equals 4 minus 8 cosine theta. So this actually might be the most standard question that was on this quiz. And let's first just graph it. So I'm going to start a new problem. So I like to start a new problem every time I have to redefine r so that I can go back to my previous work and not have to totally redo it. So it seems like we want to graph. And I'm going to graph it in polar, so that's menu 3, 5. The more you do that, the more readily you remember it. 8 cosine of, don't forget to use theta, so here. And we'll go 0 to 2 pi and see what we get. All right, so we have a negative cosine limacon. And those are actually, I think of them as the most annoying type, because when theta is 0, r is actually negative. So you actually start here, and then you trace this way, and then go all the way around, and then you finish off over here with more negative r values. So we just want to get the entire region, which meant everything that you see, including the inner loop, but we don't want to include it twice, so we got to look out for that. So I am going to graph the rectangular version of this to see what's going on. So .4 graph, and then I'm just going to use tab and r of x, and then let's change the window so I can see this thing. So it's 4 minus 8. So if I do 4 plus 8, that's 12. Well, first let's go 0 to 2 pi. And then if I go 4 minus 8 is negative 4, so I'll go from negative 5 to 4 plus 8 is 12, so let's go 13, so we're a little above and a little below. And we get this. And so if you're used to it, you know that the inner loop that we got is half of it is here below the axis, and then from this intercept to this intercept is what's generating that big outer loop. So one way to get the whole thing is just integrate from whatever this is to whatever this is of r squared. And then this is where it closes off the inner loop. So I need to find these zeros, but they're actually nice. You can do it by hand, actually, because they end up unit circle angles, but I'm going to take advantage of the fact that it's calculator. Menu 3, 1, R1 of t. Remember, you don't have to remember what it's called. You can hit var and just see them. Equals 0 for t, but I only want to do this between 0 and 2 pi, so control equals such that 0 is less than, again, I wish there was a shortcut for this, but there's actually not, t, and then here, less than 2 pi. So pi over 3 and 5 pi over 3. Like I thought, they were nice values. So let's say what we did here. We set r of theta equal to 0, and that gave us theta is pi over 3, and theta is 5 pi over 3. So we know those zeros. So one option is to just go from pi over 3 to 5 pi over 3. So one of the things you can do, which I think is really useful, is on this graph, let's change our bounds to pi over 3 to 5 pi over 3, and just make sure that gives us what we think it does. And you can see if I just go pi over 3 to 5 pi over 3, it gives me all of this, and it just never draws the inner loop. So that integral is definitely going to work. So let's write that down. So we can do 1/2, because all polar integrals have that 1/2. Pi over 3 to 5 pi over 3, and then r of theta squared d theta. That'll definitely give you the area. But we want to write two different integrals. So another option is kind of the more traditional. Well, it's not more traditional, but it's a thing that people do all the time. So if you look here, this is pi over 3, and if I go to the halfway point, that would give me half of the area, and then if I just double that, that gives me all of it. And so the halfway point is actually just pi, right? So At 0, you're over here. You kind of trace half of your inner loop. Then you go all the way out. When you get to pi, you're here. So if I go from pi over 3 to pi and then double it, that'll also give me the area. So let me do that. So we're going to double it, and then it's polar, so there's 1/2. There's the integral from pi over 3 to pi, and then r squared d theta. So that'll also work. You could go from pi to 5 pi over 3. That would work. There's just tons of options. So what I definitely recommend is that you just take advantage of the fact that you have a calculator, and if you think a set of theta bounds will work, just kind of change the bounds on your calculator. And then if you get an area, so it's calculator, so if you get about 142.1002, then you definitely have the right integrals. So you can do things where if you go from 0 to 2 pi, so for example, we go 0 to 2 pi, that's going to give us the entire graph. And in doing the entire graph, you double counted the inner loop because you count it here. So we already counted this region from 0 to pi over 3. Then as I go from, so this is pi over 3 to pi over 2 is this part in the first quadrant here. But pi over 2 to pi, at some point you count the inner loop here. So this part's been counted once as you went from pi over 2 to pi. And then as we go from pi to 3 pi over 2, we actually count this part of the inner loop again. So we've counted this part twice now. And then when we get over to here and finish the curve, we count this region again. So we actually counted the inner loop twice if we go from 0 to 2 pi. So then we'd need to subtract the inner loop. And the inner loop, you can get any number of ways. You can go from 0 to pi over 3 and double it. You can actually, so this is 0, and we hit this point at 5 pi over 3, but you could think about backing up, right? So instead of starting at 0, what if we started at negative pi over 3? So you can go from negative pi over 3 to pi over 3 and get the entire thing. There's just a lot of options. So anything that works will work. So that's about it. All right. I hope you found this helpful, and good luck.